Welcome back, everyone, to the eCoreAcademy e-learning platform. My name is AJay, back with yet another Algebra 1 video for you all. And today's lesson topic, we're going to be focusing on the quadratic equations, continuing with this unit, and we're going to be specifically looking at the vertex form of parabolas. Now, before we get into today's video, please make sure to do 4 things. Make sure to smash that subscribe button, hit that like button, turn on post notifications, and drop a comment down below. Alright, so what exactly is today's video about? The vertex form. So we're going to be discovering what the vertex form is in the intro to this video, how exactly it represents a parabola throughout the video, and basically what are its transformations. How do its different components and variables throughout its equation like a, h, and k, how does it affect the actual parabola, and how does it create your transformations like shifting it, expanding it, making it smaller, more narrow, and changing its overall location and appearance. So without further ado, let's jump right into it. So vertex form. What exactly is vertex form? Vertex form, by definition, is a quadratic equation, a form of a quadratic equation that is used to express a quadratic function by using the components of the parabola's vertex. So that's the defining feature of the vertex form. It characterizes essentially the entirety of the equation, the entirety of the parabola, by utilizing its vertex form as a definitive way of characterizing the location of the parabola and also the properties of it. Excuse me. Vertex form is written as a whole square equation that uses both the x-coordinate, and the y-coordinate of the vertex to determine coordinate relations and the vertex itself. So obviously it's using the x-coordinate and y-coordinate separately within the equation in order to help you differentiate between your x and y-coordinate that you're looking for in terms of points on your parabolas, and it also helps in determining coordinate relations, helps you easily use points, take points, and also graph them in order to create your parabola, and also it helps you identify the vertex itself, where your parabola is even going to be starting. So, vertex form and standard form are the two most common ways to express a parabola. Standard form is a little bit more, less consolidated. The vertex form has to do with parentheses, and it has to do with the whole square. Standard form is a little bit less. It's it's a little bit less, compressed. It's more drawn out, expanded form essentially of the vertex form. And of course, your standard form and vertex form can be swapped by calculation. You can literally just switch them in by creating whole squares and also factor out your whole squares to create your standard form. But we'll get into standard form in another video. So throughout this lesson, we're going to be going over, obviously, first we're going to look at what the equation is and what the different parts of the vertex form really is, and then, of course, how those different parts really affect the parabola itself and the overall transformations that this form provides. So now let's actually look at the vertex form itself, and we'll identify what the features are and what they represent. So what are the different components / variables of the vertex form, and how do they accurately represent the parabola? So this is the actual vertex form equation. It's written in the form that y is equal to a times x minus h whole squared plus k. Now realize that y is substituted for f of x. This is always interchangeable. Remember, a function is merely a characteristic of y. So let's take a look at the left-hand side. What is y? Well, y is merely your y-coordinate. What you're going to be plugging in is substituting any of the coordinates along your parabola. Then, of course, your a, we looked at a in the previous video, looking at the quadratic function basics. This is the basic transformation that we looked at, and this basically stretches or compresses your parabola. It makes it wider, or it makes it much more narrower through vertical stretches and vertical compressions. Also, if your a is positive or negative, it can actually alter, where exactly the parabola is going to be in terms of the x-axis. If it's negative, it can even reflect the parabola itself, flipping it over the x-axis, literally creating what you would characterize as a mirror reflection of the parabola. Then, of course, we have our x, which represents our regular x-coordinate of that x-y coordinate pair. And then, of course, we have our h variable, which is going to be the x-coordinate of the vertex. Remember, this is vertex form, so this is going to be representative utilizing the characteristics of the vertex. We're breaking it apart into x and y. So we're utilizing the x-coordinate of the vertex. You're going to be subtracting that from your x-coordinate. And then, of course, we're going to be adding it outside of that whole square. X minus h is going to be done first, and then you're going to whole square that whole value, and then you're going to multiply it to a, and then finally you're going to add it to k, and k would be your y-coordinate of the vertex. So once you discover what the vertex is, you basically knocked out most of what you need in order to actually calculate for different points and identifying the full parabola in Vertex. So first, we're going to go into depth with what exactly A is. Should be a simple review. I'm going to be showing a little bit more graphics to really help you get a grasp of what A really does to the parabola in our previous video about quadratic function basics. So let's go. So how exactly does A affect a parabola? So let's take a look at a simple parabola. Let's graph this parabola. The equation is going to be f of x equals ax squared. We're not going to include all the other values like h and k because we're just focused on A. And of course, f of x equals x squared being our parent graph, we're just adding a to see the direct translation. So what if we wanted to expand our parabola? What if we wanted to make it wider with its vertex at the same spot? So just making it wider while it still has the same foundational point. So how do we do that? So in order to make it wider like this, literally stretching it out, making it a vertical, essentially a vertical compression in this case, making it wider, in order to do so, it would have to be your A value, obviously, and you would have to conduct a vertical compression to make it wider. Now you might be thinking, if I'm compressing it, aren't I making it like narrower? Well, it's a vertical compression. You're going to be taking your y-axis, you're essentially just smushing down the parabola, so it's actually going to become wider, seeping out through the sides. And in order to do so, that means your A value, the absolute value of your A, has to be between 0 and 1. So it's going to be a fraction between 0 and 1, the absolute value of it. What if we wanted to do the opposite? Obviously, we want to make it narrower. So in order to make it narrower, just like our blue parabola as represented, we want to create a vertical stretch, essentially, stretching out that y-axis to make it a lot skinnier and taller and narrower. In this case, that means that the absolute value must be greater than 1. Obviously, it's going to be absolute value, so it can be a negative value with its face value, not ignoring the negative. Its absolute value being greater than 1 is actually going to create that narrower stretch, and obviously, if it's 1, it's going to essentially keep the parabola the exact same, the stretch width, essentially. And then, of course, our last transformation of A, this is going to be if we essentially take that original parabola, we flip it over the x-axis just like a mirror reflection. It still remains the same. We didn't stretch it or compress it in this case. We just flipped it over the x-axis. A does influence that. And in order to reflect it over the x-axis, just flipping it over its vertex, just flipping it over exactly, all coordinates are going to be lined up exactly. That means that A has to be less than 0. So it has to be a negative value in order to flip it as well. And just as a side note, A is going to be multiplied in your vertex form equation with x like a scale factor, and it's going to be multiplied in every equation, just like your standard form equation, ax squared. It's going to be multiplied directly to your x, so it's going to essentially be like a scale factor. It's increasing or essentially decreasing that stretch width. Now that we've gotten the basic essence of A, let's move on to the transformations of k and h, our next two variables. So how exactly do k and h affect a parabola? So first things first, we're going to create our parent graph, that being f of x equals a times x minus 0 squared plus 0. This is just a fancy way in vertex form of conveying f of x equals x squared. Remember, if you count out the 0 for our h value within the parentheses, that's merely f of x equals ax squared plus 0. You can discount the 0 as your k. This is just your parent graph. Now we're going to start creating transformations where we use k and h solely. So what if we wanted to do a basic translation? Obviously, h and k are 0, and k is also a 0, but just in those positions. H is within the the parentheses being subtracted from x, and obviously k is outside. What if we wanted to make a simple shift of this parabola? What if we wanted to shift it leftwards? We already did, stretching it wider, narrower, and also flipping it. Now the only two transformations left is moving it left and right and up and down. So obviously K and H essentially affect those respectively. So what if we wanted to move this parabola to the left? We wanted to shift it left, all of its points to the left, including its vertex, and essentially create a new parabola just like this, the red one. We didn't stretch it out or anything. It's just the same parabola. Just shift it. So in order to do so, our new equation now, since we shifted it left, is actually going to be f of x equals a times x plus 5 squared plus 0. Now, if you notice this new equation of the shifted form, it's very similar to the original equation, except for the fact that we added 5. We put 5 in place of our 0 for h, and we're adding 5. So essentially the property is, as your h increases in value, as it increases its face value, the graph starts to shift leftwards. So as you can see, positive 5, it increased 5 from minus 0. So since it increased 5, it's going to move left 5. So plus 5 is left 5. And obviously, if you wanted to move right, you're just going to do the opposite with h. So in order to move right, that means h decreases. So if you go right, essentially left on your number scale, going from 5 and decreasing, you're going to move right the opposite direction, essentially. So in order to move left, you're going to increase, you're going to have a higher value. In order to move right, you're going to decrease your value in order to move right. And that, of course, is all affected by your h value. Now, up and down, you can already guess that's both going to be affected by k. So if we wanted to move our graph, say for example, down and create this new blue graph as our transformation, the new function is essentially going to be f of x equals a times x plus 0 squared minus 5. Again, this is similar like to our original equation, except that we replaced our k of 0 with negative 5. So essentially all we did was we added the negative 5 and we shifted down 5 units. So unlike your h value, whenever you're shifting down, whatever the face value is, negative 5, negative means you're moving down. So as k increases, the graph, as k decreases, I apologize. That should say decreases. So as k decreases in its face value, not just its absolute value, but as k decreases in its face value, the graph will shift down. So like negative 5, you went negative 5 leftwards on the number line, so you're going to go down 5 units. And obviously the opposite being when you're going to increase that value, going rightwards on the number line, you're going to go up. You're going to move up positive units when it's a plus sign. All right, now for our final slide, we're going to essentially practice a very valuable skill, and this is going to be essentially plugging the vertex into your equation using vertex form in order to calculate for your a value, to take a parabola and literally transform it with all the information into a vertex form equation. So we're going to do the reverse. So we're going to discover the value of a when given a graph. So we're given this graph here, this parabola, this graph, and we're given that the vertex is going to be 3, 0, and we're also given another point on the parabola, 4, 2. Now, in order to create an equation of a parabola, you always need 2 points. One of them being vertex form, one of them being your vertex specifically for your vertex form, and also another subsidiary point like 4, 2. And this is all that we need in order to create our actual equation, our full equation with our a, h, and k, the 3 variables that we're calculating for. So let's start off with our basic vertex form equation. F of x equals a times x minus h squared plus k. So the first thing that we know that we have the vertex. That's going to be our h and our k already knocked out. Excuse me. So now we have f of x equals a times x minus 3. Obviously, we're going to subtract our x value, in this case, our h. And then, of course, we're going to add it to 0 because 0 is our y-coordinate for our vertex. Now, the only thing that we have to calculate for, is a. It's nowhere given on the graph traditionally, so we actually have to computate and calculate for it. So in order to do so, that's where the other subsidiary point comes in to play, essentially, 4, 2. So we're essentially, excuse me, so we're going to plug in 4, 2 into our equation, replacing the f of x, our y, with 2, and obviously we're going to replace the 4 inside of our equation. So now we're just basically going to plug 4, 2 into our equation, 2 substituting our f of x, our y-coordinate essentially, and then 4 substituting for our x-coordinate, our 4. So when we calculate that out, 4 minus 3 is 1, 1 squared is 1, so then we're left with a times 1 being a, so we're left with the equation 2 equals a plus 0, 0 cancels out, so that means that we're left with the final equation that a is equivalent to 2, just basic computational math. So since we know that a is equal to 2, we're actually finished with our equation. We can plug all those values in, our a, our h, and obviously our k. So now we have that f of x equals 2, our a value, times x minus our h, 3 squared. And since k is 0 and our vertex 3, 0, we're just not going to include it just to keep it more concise. So that's basically our final equation of this graph. All right, everyone. I hope you guys enjoyed this video. This has been the eCoreAcademy e-learning platform. Please make sure to like and subscribe down below. And also, feel free to drop a comment. We really do pay attention to feedback. Also, please make sure to check out our website at www.ecoreacademy.org. Email us at eCoreAcademy@gmail.com. And also check out all of our socials, Pinterest, Facebook, Twitter, Instagram, and TikTok, all linked down below. This has been AJay Raj. I had a blast making this video. And I hope I see you all in the next video and next couple videos to come with this quadratics unit. So please stay tuned. Peace.